Hi everyone, welcome back to this channel. Today we are going to model a RC beam using a finite element software called Abaqus, and we will be using two different approaches, two-dimensional and three-dimensional approach. And at the end we will compare the results from those two approaches. For that we have taken an example of a RC beam called VSA3 from the paper of Vecchio and Sims. All the cross-section properties, reinforcement details, concrete details are taken from this paper. This paper can be found in the internet as its title is Experimental and Analytical Re-examination of Classic Concrete Beam Test by Vecchio and Sims. So here there are 12 beams, and in this video we are modeling A3. So this is the cross section, rebars M10, T4, M25, M30, and all reinforcement details and concrete details are listed here. On the right side is an experimental setup. We will follow the same setup in the modeling. So let's go into the modeling part. So first we are going to model a beam using 2D approach, where we will model a strip of a beam element by 2D plane, and we will define the thickness of the 2D plane element. So in Abaqus, when we model the beam, we will simply follow these steps one by one. So at first part, we define concrete element, which is a 2D plane element. It's a loading plate. Actually, this is a steel plate. We will be using it as a steel support at the supporting point and at the loading plate as a loading point. Similarly, the rebars, which is modeled as a wire and truss type, and it's simply a horizontal linear line. So M25 also similar, M30, and the stirrup. Since in 2D approach, we are more concerned with the vertical leg of stirrup. So for vertical leg is here modeled, not the horizontal one. Once we define our parts, we define the property. So for concrete, here we define elastic and nonlinear property for concrete. So in elastic, Young's modulus value and Poisson's ratio is defined, which is taken from the paper, and concrete stance plasticity. Plasticity parameters are defined, compressive behavior is defined, and tensile behavior is defined. Similarly, for loading plate, which is steel plate, only elastic property is defined. Young's modulus of 200,000 megapascal and Poisson's ratio of 0.3 is defined. For rebar, we define elastic and plastic. So in plastic, we define the nonlinear data. And in elastic, we simply define Young's modulus and Poisson's ratio values. For M20 as well, M25, sorry, it's elastic and plastic. For M30, it's elastic and plastic. For stirrup also, it's elastic and plastic values are defined. Once we define our property, we will define the cross-section. Since we define concrete as a 2D element, we have to define its thickness, which is along the z direction, and the Abaqus will consider this value while computation. Also for the loading plate as well, which is 2D plane element, here the thickness is defined. For reinforcement, we define it as truss element, and we will define or assign the cross-sectional area of the rebar. So once we define the cross-section, we will assign the cross-section to our parts. So here, so this is the stirrup. We will assign it as a stirrup. Similarly, we will assign for concrete as well. Since it is already assigned, it looks green. If it is not assigned, it looks white as shown here. So from here we can see that already the concrete section is assigned. Also for loading plate as well assigned, and rebars as well assigned. And the third step is to assemble all the parts. So here we can see that the concrete material is here, the loading plate, steel support, rebars and vertical stirrup all are assembled as shown in the paper. We can see here in the paper the assembled detail. Sorry. So we assembled according to this. And the fourth step is to define step. The procedure is static and general, where the load will be applied in a static manner, and we will define the increment of our loads. So total number of increment is 10,000, initial increment size is 0.01 and maximum is 0.1. Once we define step, we will define interaction. Interaction is the bond type or contact type between the elements. So the coupling is it is that we will define a reference point which is RP1, and it is coupled with the loading plate by this coupling type of constraint. So when we apply the load at this point RP1, it will be transferred to the load plate because of this constraint type. Similarly, we have defined embedment for the bonding of reinforcement and concrete. So the embedded region is reinforced concrete, which is red, and host region is concrete, which is pink color or magenta. The tie type is the contact type between the concrete and steel plate. So red is master surface, which is concrete, and the pink one is a slab surface, which is steel plate. Similarly for loading plate as well, master surface is concrete and slab surface is loading plate. So these all are 2D elements. And after that we define load. So we apply load here in this point, and we define also boundary condition. So on the left side, it is defined as a pin where we restrain the displacement along x-axis and y-axis, which are u1 and u2. On the right side, it is roller, so where displacement is restrained along y direction only. Once boundary conditions are defined, we will mesh our structure. Here we can see the structure is meshed, and then we will now we will run our model. So we will create a job and we will run it. So we submit this job. So it is submitted. Now the model runtime is finished and we will check the results. We can see the load deformation curve from here. From field output, we can select the reaction force RF2, which is in y direction, and U2. And we'll select the load, the node set RF where we have applied the load, and we will plot it. So it's almost done, and now it will plot the load deformation curve. Here we can see the load deformation curve. So the ultimate load capacity is around 380 kilonewton, and its corresponding displacement is around 40 millimeter. Also, we can check the deformation and stress distribution as well. So here it is stress distribution in the concrete. We can see the top of the concrete is already crushed. Also, we can see the stress distribution in rebar as well. So here we can see stress distribution in rebar. We can see some vertical stirrups are yielded already. Now we will continue our modeling with 3D approach. So we will open our another Abaqus interface. This is 3D modeling in Abaqus, where we define our concrete model as a 3D. And similarly also the rebars, they are defined as wire element truss type M25, M30, and the steel plate, it is in 3D. We have defined its length, width, and the depth. Also the stirrup, now we have vertical legs as well as horizontal legs. Once we define parts, we will define the property, which is very similar to that of we have defined earlier in 2D approach. So we'll define concrete property, its elastic and plastic property. The rebar property as well, we define its elastic and non-elastic property, or that is the plastic property. Similarly for M25, elastic and plastic property. M30, it's elastic and plastic. For steel element, which is steel support and loading plate, we only define elastic property since we are not concerned with its deformation. For stirrup, we'll define its elastic and plastic property. After then, we define the cross section here. So for concrete, it is defined as a solid homogeneous. If we did, we only define the concrete cross section. Here we don't define the plane element thickness because it is already in 3D. We have already modeled its 3D dimensions, so we don't need to define thickness here, which we have defined earlier in 2D. We have defined thickness, but for 3D we don't need that one. For rebars, we define the cross-section areas, and here it is if you remember earlier for M10 it was 300 because it was the total sum of reinforcement, but here in 1D we will give the cross-section area for each rebar since we are assembling 3 rebars. So individually there are 3 rebars, so we only define cross-section area for 1 rebar. And also steel, we don't define thickness, we only define the section for steel material. Also for stirrup as well, we define the cross-section area just for the cross-section area. So in 2D, what we define is the area for total vertical legs. So if there were 2 vertical legs, we define it as 64, but for 3D, we only define the cross-sectional area. So that is the difference when we define our cross-section, and then we will assign this cross-section to our element or parts. So for example, concrete, here already the element is assigned. We can select concrete since it's already assigned, so I will simply cancel it. We will assign for rebars as well since it is green section already, green color, so it is already assigned. If it is not assigned, it appears as a white of the stirrup. And the third step is to assemble everything. Here we can see loading plate, concrete element, and steel support. If we see by color or see by part, then we can see here in 3D. So concrete element and the stirrup, the rebars, we can see that. So once we assembled, then we will define our load step. Here we will define a static general procedure, and we will define the load stages and increment size as similar to that of in 2D. So minimum or initial increment size is 0.01, maximum is 0.1, and total number of increment is around 10,000. The interaction type is also similar to that of in 2D. Coupling, since we have the RP1 is a point where we apply the loading, so it is coupled with its plates. And embedment type is for embedding the reinforcement in concrete cross section. So embedded region is it appears as a red, which is reinforcement, and the host region is the pink color, which is concrete. Similarly, for steel support and loading plate, we define as a tie. We can see here. So the concrete is a master surface, which is red, and loading plate is a pink one. You can see here, with a slip surface. So once we define interaction, we will define load. So load is applied, which is displacement. So it is displacement control load. And also the pin and roller support boundary conditions are defined. So in the pin support, direction along y-axis, x-axis, and z-axis, that is u1 is x-axis, u2 is y-axis, and u3 is z-axis. So they are restrained. And for pin as well, the displacement along y-axis, which is u2, is restrained. So this is how we define our boundary condition. Once we define load, the final step is to mesh. So here we have meshed our structure. Finer the mesh, better will be the result. And the third part is to define job, where we run our model. Let's say it is VSA3 and 3D. So now here we will submit the result. And we can also monitor our process from here. So here we have some error. We can, it says some removal of file. We'll delete it and we will see what is our error. So here we will discard the old edits. And now we will run again. Okay, so now it's running. So we finish our modeling. Now we'll go for result. Let's see the load deformation curve for 3D result. So we will select F2 direction, Y2, U2 direction, and node set of this. And here it is our load deformation curve. Now we can compare this result with 2D. We can export this result in Excel file, and we can compare this with 2D. So 2D and 3D results are already plotted here. We can see that the initial stiffness, they are quite same, But the ultimate load capacity of 3D is higher than that of the 2D, and the error is around 10.5%. Also, we can compare the stress distribution of 2D and 3D side by side. So on my left it is 2D and on my right it is 3D. So we can see that the stress distribution are quite similar to that of 2D and 3D. So on the board modeling, we can see the stress distribution. The concrete at the top is crushed, or it exceeded the ultimate strength in 2D and in 3D. Also, we can see the stress distribution for reinforcement as well. So on my left it is 2D and on my right it is 3D. And we can see the stress distribution is also quite similar in both cases. So on both sides, in both we can see some reinforcement are yielded, the vertical stirrups. So thank you so much guys for your attention. We have seen the results of 2D and 3D modeling for RC beam in Abaqus. Also the load deformation curve as well. We have seen that both has similar nature at the beginning, but the ultimate capacity of 3D is higher than that of the 2D. So that's all for this video, and thank you very much for watching our videos. Please subscribe our channel so that you will not miss our new videos in the future. Thanks a lot.